So now let's go ahead and talk about some of the other considerations when using visitor. And this will give us a chance to talk about the pros and the cons and so on. So some of the nice things about this pattern is it's very flexible. So you can have visitor operations like print and eval and optimize and analyze and so on and so forth. Those are all decoupled, largely decoupled from the object structure. They just have to know what the elements in the object structure are. As you can see in this case, these would be the various subclasses that implement the component node abstract base class. So if you look on the left-hand side, you can see that we have all the visit methods, and they all correspond to the different subclasses in the hierarchy. In this environment, with this model, adding new visitor implementations like a new analysis visitor or a code generator visitor or whatnot won't do anything at all to the composite structure of the expression tree. So that part is stable, and the visitors can vary, which is exactly what we're trying to do. We also get this nice separation of concerns. We localize the functionality in the visitor implementation. So, for example, if you visit a leaf node, then that's going to be localized to the leaf node's accept method. All that code is tucked right in there, and that's where you have to put the logic, and then that double dispatches back to the visit method on the visitor. Same thing with composite add node. When you visit this, it knows how to go visit the appropriate method. And that's using the static polymorphism or the method overloading features in C++ or Java. There are some downsides, though. There's this tight coupling, so there's a circular dependency between visitor and element interfaces. So if you add new subclasses to the composite hierarchy, like you add composite mod node, as we do here, then you'll have to go through and add the corresponding visit method to all the visitors. So making changes to the object structure causes a lot of rework in your existing visitors. And that's why you really need to apply this pattern most commonly when the object structure rarely, if ever, changes, but the operations change, because this causes ripple effects that can be tedious and error-prone to deal with. From an implementation point of view, it uses double dispatching, which is just saying that you use the static and dynamic polymorphism to avoid having to do downcasting. And as you can see here, it can figure out what to do based on two method calls, one from the leaf node or the composite hierarchy subclass node to the visitor, and then from the visitor back to the corresponding way of handling that method in the visitor. So this is what's called double dispatching. And there's a nice description of double dispatching in the link at the bottom of the page. You also need to decide how you want to design your visitor API. Do you want to have a visit method for every meaningful subclass in the object structure, in the composite, like our expression tree? Or do you want to have just a handful of visit methods that are working on more general types? The trade-off is between generality and specificity, and between enumerating all the different elements, which can break if the object structure changes, versus having to do dynamic downcasts or dynamic casts in your visitors. My preference is to enumerate them, because this is most commonly used when the object structure doesn't change very much. So you're perfectly justified in doing that in most cases. There's a lot of different known uses of this. There's an interesting use of the visitor pattern in Java with its NIO file visitor class, where you can pass visitors in, and they're called as the method walks the file tree. So as you walk through the file tree, then you can go ahead and define a visitor that'll do different things depending on what you encounter as you're walking through the file tree. And then we've also applied it in a lot of our middleware dealing with something called the interface definition language, which is a language-independent, platform-independent way of describing data structures and data types with various methods and fields and so on. And the way that the interface definition language, or IDL, works is it has this language-independent syntax, which can then be mapped to different concrete programming languages like Java, C++, C, Python, Ada, whatever you're trying to map to. And to do this, we basically have a compiler that parses the IDL files, builds an internal syntax tree, and then it goes ahead and uses the visitor pattern to walk through the nodes in the tree, printing out the elements as it goes, or generating the code as it goes. And so to implement a different visitor for a different concrete language, you just have to implement an abstract factory, one for every type of node that you have, and then go ahead and use the visitor pattern to visit the elements and generate the appropriate code. So it's very clean, very cool. And if you take a look at the paper at the bottom of this page, you'll find out more about using the visitor pattern in this context. So in our example, we use visitor together with iterator and strategy to traverse our composite-based expression tree in a very flexible and extensible manner in order to perform the designated operations. So as you see here, there's a lot of patterns involved. So we've got iterator to iterate through every element in the tree in some traversal order. We have the factory method pattern that creates the iterators. We use strategies for the different traversal ways of traversing the tree, different traversal algorithms. We use the bridge pattern to encapsulate all the machinery behind a nice, simple, common API that never changes, even if the expression tree changes. And then, of course, we use the visitor in order to be able to apply operations to those things. So this is a really nice example of high pattern density, and it also makes it easy to simplify adding new operations because nothing in the tree changes. And of course, we've long since kind of fixed the set of operations in our tree, not operations, the operands, the types in the tree. And this would only cause problems if we needed to add new kinds of tree operations, not operations on a tree, but things like modulus or bitwise or anything else you're trying to do that would change the arithmetic capabilities of the expression tree functionality.